In an open delta system, specifically one operating at 120/240 volts, three-phase with lines loan, L2, L3, neutral, and ground, and where the 120-volt loads consist of lights and receptacles, the application of National Electrical Code Article 310.15 B4 regarding neutral conductor ampacity is indeed relevant. In an open delta configuration, the neutral conductor's role in carrying current differs significantly from its role in a standard three-phase, four-wire system. The critical distinction lies in understanding how balanced or unbalanced loads impact current flow in the neutral conductor. Firstly, it's important to define an open delta system. This type of three-phase system is derived from two transformers, unlike a closed delta which uses three. The open delta configuration is less efficient than a closed delta, but it offers a cost-effective solution when a full three-phase capacity is not initially required, or when one transformer in a closed delta bank fails. The voltage relationships in an open delta are such that you obtain three-phase power, but the available power is only 57.7% of what a similarly sized closed delta bank could provide. The 120/240 volt aspect indicates that the transformers are center tapped, providing both 240 volts for three-phase loads and 120 volts for single-phase loads such as lighting and receptacles. The designation loan, L2, L3 refers to the three-phase lines, neutral to the neutral conductor, and ground to the grounding conductor, all of which are essential components for safe and effective power distribution. Now, addressing the neutral conductor. In a balanced three-phase system, the current in the neutral conductor is theoretically zero because the phase currents cancel each other out. However, in reality, perfect balance is rarely achieved. Single-phase loads connected line to neutral cause current to flow in the neutral conductor. In an open delta system, the behavior of the neutral conductor is unique because the system is inherently more susceptible to imbalances, especially when single-phase loads are connected unevenly across the phases. This brings us to National Electrical Code Article 310.15 B4. This section of the code addresses situations where the neutral conductor does not carry significant current. Specifically, it states that a neutral conductor which carries only the unbalanced current from other conductors of the same circuit need not be counted when applying the adjustment factors in 310.15 cone. The adjustment factors in 310.15 cone relate to directing conductors based on the number of current carrying conductors in a raceway or cable. If a neutral conductor is not considered a current carrying conductor, then it does not contribute to the directing requirement. The key to applying this article correctly is determining whether the neutral conductor carries only the unbalanced current. If the 120-volt lighting and receptacle loads are evenly distributed across the three phases of the open delta system, the neutral current will be minimal. In this scenario, National Electrical Code Article 310.15 E4 would indeed apply, and the neutral conductor would not need to be counted as a current carrying conductor for ampacity adjustment purposes. However, if the loads are significantly unbalanced, the neutral conductor will carry a substantial amount of current, potentially exceeding its ampacity if it were sized based only on the assumption of balanced conditions. It's crucial to perform a load calculation to determine the maximum possible unbalanced current that the neutral conductor might carry. This calculation should take into account the types and quantities of 120-volt loads connected to each phase. If the calculated neutral current is significant, National Electrical Code Article 310.15 B4 would not apply, and the neutral conductor must be counted as a current carrying conductor. Now, let's consider Table 310.15 B2. This table provides ampacity ratings for conductors based on their insulation type and ambient temperature. It is a general table used to determine the allowable ampacity of conductors before any directing factors are applied. In the context of an open delta system, the relevance of Table 310.15 B2 depends on whether the neutral conductor is considered a current carrying conductor. If National Electrical Code Article 310.15 B4 applies and the neutral is not counted, then Table 310.15 B2 is used only to determine the ampacity of the phase conductors low L2 and L3, which are always considered current carrying. However, if the neutral conductor does carry significant unbalanced current, it must also be included when using Table 310.15 B2 to determine the overall ampacity requirements of the conductors. In summary, when dealing with a 120/240 volt open delta system powering lighting and receptacles, the applicability of National Electrical Code Article 310.15 B4 hinges on the balance of the loads. If the loads are well balanced, the neutral conductor does not need to be counted as a current carrying conductor, and Table 310.15 B2 is used only for the phase conductors. However, a careful load calculation is essential to verify this assumption. If the loads are significantly unbalanced, National Electrical Code Article 310.15 B4 does not apply, and the neutral conductor must be counted, affecting the overall ampacity calculations. It is always prudent to err on the side of caution and consider the neutral conductor as current carrying unless there is clear evidence of balanced loading. Furthermore, local electrical codes and regulations should always be consulted, as they may have additional requirements or interpretations regarding neutral conductors in open delta systems. It is also necessary to consider voltage drop calculations for both the phase conductors and the neutral conductor. Excessive voltage drop can cause problems with equipment performance and can even be a safety hazard. The neutral conductor should be sized to minimize voltage drop, especially if it is carrying a significant amount of unbalanced current. Grounding is another critical aspect of open delta systems. Proper grounding ensures that fault currents can safely return to the source, minimizing the risk of electrical shock and equipment damage. The grounding conductor should be sized according to National Electrical Code Table 250.122, which is based on the size of the overcurrent protection device protecting the circuit. In addition to the general requirements for grounding, open delta systems may have specific grounding requirements depending on the configuration and the type of load served. For example, if the open delta system is derived from a corner grounded delta transformer, the grounding requirements will be different than if it is derived from a center tapped transformer. Regular maintenance and inspection of open delta systems are also essential to ensure their continued safe and reliable operation. This includes checking connections for tightness, inspecting conductors for damage, and testing the grounding system to verify its effectiveness. Any problems that are found should be corrected promptly by a qualified electrician. Open delta systems can be a cost-effective and reliable solution for powering three-phase loads, but they require careful design, installation, and maintenance. By understanding the unique characteristics of open delta systems and following the applicable electrical codes and regulations, it is possible to ensure their safe and efficient operation. Understanding the implications of unbalanced loads on the neutral conductor is paramount in ensuring the system's integrity and safety. Moreover, remember that electrical codes are subject to change, and it's crucial to stay updated with the latest revisions of the National Electrical Code and any local amendments. Consulting with a qualified electrical engineer or licensed electrician is always recommended when designing or working on electrical systems, particularly those involving open delta configurations. This ensures compliance with all applicable regulations and best practices, minimizing the risk of electrical hazards and ensuring the long-term reliability of the electrical installation. Also, ensure all electrical work adheres to occupational safety and health administration standards to prevent injuries or fatalities during installation and maintenance. Always de-energize circuits before working on them and use appropriate personal protective equipment such as insulated gloves and safety glasses. Before commissioning the open delta system, conduct thorough testing to verify that all components are functioning correctly and that the system is properly grounded. This includes testing the voltage and current levels on each phase, as well as performing insulation resistance tests to identify any potential insulation faults. By taking these precautions, you can ensure the safe and reliable operation of the 120/240 volt open delta system, providing power to lights and receptacles while adhering to all applicable electrical codes and regulations. Finally, remember that continuous monitoring of the load balance and neutral current is advisable, especially in systems where load variations are frequent. Installing a monitoring system can provide early warnings of potential imbalances, allowing for proactive measures to be taken before problems escalate. This not only enhances safety, but also contributes to the overall efficiency and longevity of the electrical system. Consider incorporating surge protection devices to safeguard against transient voltage spikes that can damage sensitive electronic equipment connected to the system. Surge protection devices should be installed at the service entrance and at any critical load locations. Regular inspections of these devices are necessary to ensure they are functioning correctly. The proper selection and installation of overcurrent protection devices, such as circuit breakers and fuses, is also crucial. These devices are designed to protect the conductors and equipment from overload in short-circuit conditions. The overcurrent protection devices should be sized according to the ampacity of the conductors they are protecting and should be coordinated to ensure selective tripping. When working with open delta systems, pay special attention to the transformer connections. Ensure that the connections are tight and properly insulated. Loose connections can cause overheating and arcing, which can lead to equipment failure and fires. It is also important to verify the transformer polarity to ensure that the voltages are correct. In addition, consider the ambient temperature in which the transformers are installed. High ambient temperatures can reduce the transformer's capacity and lifespan. If the transformers are installed in a hot environment, it may be necessary to provide additional ventilation or cooling. The open delta system's performance should be periodically evaluated to identify any potential problems or areas for improvement. This evaluation should include a review of the load balance, neutral current, voltage levels, and transformer temperatures. Any abnormality should be investigated and corrected promptly. Furthermore, ensure proper labeling of all electrical panels and equipment to clearly identify the circuits and components. This helps prevent accidental disconnection or energization of the wrong circuits and facilitates maintenance and troubleshooting. Consider using a color coding system for the conductors to further enhance safety and clarity. For example, you could use black for phase conductors, white for neutral conductors, and green for grounding conductors. This can help prevent confusion and reduce the risk of electrical shock. Provide adequate lighting in electrical rooms and work areas to ensure safe working conditions. Poor lighting can increase the risk of accidents and errors. Regularly train personnel on the safe operation and maintenance of the electrical system. This training should include information on the hazards of electricity, the proper use of personal protective equipment, and the procedures for responding to electrical emergencies. Keep accurate records of all electrical work performed on the system, including inspections, tests, repairs, and modifications. These records can be valuable for troubleshooting problems and planning future maintenance. By following these guidelines and best practices, you can ensure the safe, reliable, and efficient operation of your 120/240 volt open delta electrical system.